Hi everyone, today we're covering topic 2.1, types of chemical bonds. So chemical bonds form to achieve some sort of a lower energy state. And we have three basic types: ionic, which is electrostatic interactions between two ions, so Na and Cl for example; covalent, which is sharing of electrons like in H2, or in something like NH3 or water; and metallic, which is free electrons being used to hold different metallic atoms together. And they form based on electronegativity and atomic structure. We've discussed electronegativity before in Unit 1, but essentially the ability of an atom to attract electrons to itself. So as you go to the right, this electronegativity increases, and as you go up, electronegativity also increases. And so fluorine is the most electronegative. The noble gases, of course, do not have any electronegativity because they don't attract electrons to themselves. And cesium or francium are typically the lowest electronegativity. Now, polarity, which we've discussed as well, arises from differences in electronegativity. And so bond polarity measures how equally or unequally the electrons are shared in a covalent bond. If it's nonpolar, they're equally shared. In something like Cl2, for example, it's Cl and Cl. That would be the Lewis structure. And as you can tell, the electrons are shared equally because they don't have a difference in electronegativity. For a polar covalent bond, something like HCl, they're shared unequally. In this case, the electrons prefer to go to the Cl, and so Cl is slightly negative, and H is slightly positive. And generally, based on these differences in electronegativity, we can tell whether or not it's polar, nonpolar, or ionic. If it's more than 1.8, it's typically ionic. If it's between 0.4 and 0.8, and 1.8, it's typically polar covalent. And if it's anything less than 0.4, it's normally a pure covalent bond, or in other words, a non-polar covalent bond. Now, ionic bonds typically happen between a metal and a non-metal, and again, the difference in electronegativities has to be, I'll call them delta En, has to be greater than 1.8. And so generally, you only get those big differences if you have a metal and a non-metal binding together. Electrons are essentially transferred from the cation, the positive, to the anion, the negative charge. So in here, the Na will become my cation that gives an electron to Cl. I end up with Na plus and Cl minus. So the one that gives up the electron has a low ionization energy, and the one that gains an electron has a high electron affinity. Some properties of these ionic substances is they form crystals. We typically call these lattices or a lattice, and that's because they are essentially alternating in the crystal structure. And so you'll have a positive, then negative, positive, negative, and this will form a nice crystal. They have high melting and high boiling points. They're typically hard. They're brittle, so they're easy to break apart. And when they're dissolved or melted, they will conduct electricity. Covalent bonds are typically between two nonmetals. In this case, the electrons are shared between the atoms instead of just completely given up. And there's several different electrostatic interactions that can happen. You can have attractions between electrons and nuclei. You can have repulsion between electrons and repulsion between nuclei. In order for a bond to form, the attractions have to be greater than the repulsions. So you can see in this diagram right over here, right, the negative and the positive, those will attract each other, but the two nuclei themselves will repel. Same thing with the electrons. You essentially need these attractive forces to be greater than the repulsive forces for these these two atoms to actually bond. Covalent compounds are pretty much the opposite of ionic, so they have really low melting and boiling points. They're typically liquids or even gases at room temperature. If they are a solid, it's soft and brittle instead of hard. They are poor electrical and thermal conductors compared to ionic compounds, and they just basically don't conduct any electrons. The last type of bonding we can have are metallic bonds. You can think of this as basically a sea of electrons. You have some sort of metal ion, and these are spaced apart equally. And then all throughout, we have a bunch of electrons that can move throughout the entirety of this little piece of metal. And so you essentially can think of it as a group of cations suspended in a sea of electrons. It can be just one type of metal, or it can be more than one type of metal, which we'll typically call an alloy, and we'll look at different types of alloys in a second. Typically, they are high electrical and thermal conductors. They are ductile. In other words, you can turn them into wires. They're malleable. In other words, you can pound them into sheets. And generally, the IMF is stronger when there are small metallic cations. and when there are more valence electrons. And so these forces are a lot stronger, at least the metallic bonds are stronger, when you have smaller metallic cations and when you have more valence electrons. It might not surprise you that because of this, the transition metals make really good metallic bonds because they have d orbitals, which have a lot of valence electrons, and they also generally are smaller as you get smaller when you go to the right of the periodic table. And finally, some properties. They're really shiny. Again, they're malleable and ductile. You can pound them into sheets or turn them into wires. They conduct heat and electricity as they are. Metallic oxides are often basic, and they lose electrons to form cations typically. Finally, here is just kind of a big table that goes over all of that. These are things that we covered based in chemistry and honors chemistry, and so they're not necessarily new. And you should have these pretty much in your memory of ionic bonds have high melting points, soluble in water, conductive when dissolved, and they're crystalline. Covalent bonds are pretty much the opposite of ionic bonds, and then metallic bonds are somewhere in the middle, right? They have a high melting point typically, they don't dissolve, they're conductive as a liquid and a solid, and they're typically shiny and ductile. That's all for this video. Thanks, guys.